Let's continue. In the last session, we have completed this formation of tribromophenol derivatives. We understood about why this nitro group is present at this position or in this position. We also dealt about this Kolbe's reaction where you convert the phenol into salicylic acid. We completed Reimer-Tiemann reaction where we converted the phenol into salicylaldehyde. Today, let's continue. Reaction of phenol with zinc dust. Very prominent reaction where you can convert phenol into benzene. When you treat phenol with zinc, you can see the zinc is taking this oxygen as zinc oxide and it becomes benzene itself. Okay.
Yes, ma'am.
Let's do a conversion here. Give me the products.
Ma'am, A is benzene
Yes, A is
plus
benzene.
xerenol.
Okay.
Um, C is um, hydroxybenzene, benzoic acid.
That's right. Salicylic acid. That's right. Mm.
And B is salicylic aldehyde.
That's right. Very good. And name the reaction.
Reimer-Tiemann reaction.
Reimer-Tiemann. Then
Um,
Kolbe's reaction.
yeah.
Okay. For board exam, when it comes into 5 mark section, they may ask you to just uh, explain Reimer-Tiemann reaction for 1 mark. In that case, how do you produce your answer? They don't want all your paragraphs here. All they need is your reaction. So I take phenol, I treat it with chloroform, aqueous sodium hydroxide. This is my intermediate. I treat it with sodium hydroxide where this 2-chlorine upon nucleophilic substitution followed by dehydration gives me aldehyde. I acidify it so that I get salicylaldehyde. Similarly, for Kolbe's reaction, you start with phenol, treat with sodium hydroxide, ONA, CO2 and H+. You get salicylic acid. Okay.
Okay,
Next
ma'am.
Yes,
reaction
ma'am.
is oxidation reaction. You have phenol. You treat this phenol with dichromate and sulfuric acid. In other words, I say I'm treating sodium dichromate in the presence of H plus acid medium. It's a very powerful oxidizing agent which leads to the complete oxidation of this reactant to form benzoquinone. Oxidation of phenol with chromic acid produces a conjugated diketone. This is a diketone. I can see 2 ketonic group are there. They are in conjugation as well. You can see they are in conjugation, isn't it? So it's a conjugated diketone called as benzoquinone. In the presence of air, phenols are slowly oxidized to dark colored mixtures containing quinones. So if you keep phenols in air, okay, so what happens here? They get converted into quinones. What are quinones? This is quinone. Benzoquinone, that only they are mentioning here. So either you have to use this to form benzoquinone, or you just keep it in air, they will form dark colored mixture containing quinones. So what we have completed till now is the reactions of the phenols. To sum up the reactions of phenols or the alcohols from our previous session. Alcohol in the presence of HX, hydroacid gives RX. We learnt about Lucas test, HCl in the presence of zinc chloride, where tertiary alcohol gives immediate turbidity. Reaction with phosphorus trihalide PX3, ROH when I treat it with PX3 gives me RX. Dehydration reaction, when I treat it with sulfuric acid at high temperature, it leads to elimination of water, which is called as dehydration. Can also be carried out in the presence of phosphoric acid, anhydrous zinc chloride, alumina, P2O5 or P4O10. If I do the same reaction at 413 Kelvin, I mentioned you will be forming ether. Ether formation will happen here. You can see the secondary alcohol needs lower temperature and lower concentrated phosphoric acid to do the reaction. Tertiary alcohol needs much more less concentration and low temperature to form the alkene. This shows the stability order of the tertiary followed by secondary followed by the primary alcohols. Oxidation reaction. Primary alcohol first initially gets oxidized to aldehyde, further to pure acid. In order to have mild oxidation, you can use chromium trioxide in anhydrous medium. We learnt about the reagent PCC, pyridinium chlorochromate, where you convert the primary alcohol into aldehyde. You can see the secondary alcohol here. Secondary alcohol, whatever, whether you use strong oxidizing agent or mild oxidizing agent, it will stop with ketone itself. No further oxidation can happen. Tertiary alcohol do not get oxidized at all. Instead, if you are going to use stronger oxidizing agent at elevated temperature, the cleavage will happen. Breaking of the CC will happen to give different carboxylic acids. Many mixtures of carboxylic acid will get with less number of carbon atom. The next catalyst we saw was copper. You can see primary alcohol to aldehyde, secondary alcohol to ketone. You can see it is not stronger here. It does not promote acid here. If I take tertiary alcohol, you can see it is undergoing dehydration reaction. In the previous two cases, it was dehydrogenation reaction where you just removed hydrogen. In the presence of copper, tertiary alcohol gives you dehydration reaction. We learnt about this aldehydes and formaldehyde, methanol or methanol, CH3OH, which is becoming fatal due to the formation of formic acid. And this alcohol is called as denatured alcohol. We went on to study about the EAS reactions of the phenols here, where you can see the phenol in the presence of dilute nitric acid gives mixture of product ortho and para. Here, ortho can form intramolecular hydrogen bonding, so it will be boiling at first. Therefore, you go for steam distillation. It is steam volatile. Then in the presence of corn HNO3, you can see this trinitro substituted product, which is white in color or colorless. The name of the compound is picric acid. If at all I'm using bromine in the presence of carbon disulfide, you can see I'm having two products here. Due to steric factor, para product is a major one here. We also learned in order to halogenate phenol, you don't need FeBr3 catalyst at all because phenol itself, OH itself is a very good activator so that the Br plus can directly come and attack the benzene. When phenol is treated with bromine water, that means Br2 in the presence of water, protic solvent, you can see 3 bromo substitutions are happening at a time. It is also a white precipitate. So we have completed the reactions of phenols till now. Okay. Let's work at give the structures and products you would expect when each of the following alcohol reacts with HCl in the presence of zinc chloride, HBr and SOCl2. Let us do 2-methyl butane 2-ol. First build the structure 1, 2, 3, 4. Second position I am having OH. At the same second position, I am having CH3 as well. So this is the structure of it. I treat it with HCl in the presence of zinc chloride. What should happen? Protonation will happen so that it will become plus OH2. You will remove this water, isn't it? Remove the water. Now you'll have CCC, C, CH3, CH3 plus. What kind of a carbonium? Tertiary carbonium. So how am I going to, what should happen next? I'm having chloride here. Because H plus only participated, I'm having chloride. Now the chloride will come and attack this spot. Do you understand, both of you?
Yes, ma'am.
Yes,
Right.
ma'am.
Same thing happens with respect to HBr as well. Instead of chlorine, I will have Br substitution here. Thionyl chloride. We have learnt already alcohol plus thionyl chloride will give you RCl. So here, what would happen? Chlorine will get substituted here. Understood, right?
Yes, ma'am.
Yes, ma'am.
Predict the major product of acid catalyzed dehydration of 1-methyl cyclohexanol. Let's draw the structure of 1-methyl cyclohexanol. I want you to complete this question. Diksha will answer it, okay? Hmm.
Ma'am, I have a doubt though. Isn't
Hmm.
that only cyclohexanol? Don't we also have to add 1-methyl?
I didn't draw the structure. It's incomplete. I'm waiting for Diksha to complete it.
Oh, okay.
Ma'am, is it 1-methyl cyclohexene?
Very good. That's the right answer. That's right. You're having 1-methyl cyclohexanol here. This is the structure of 1-methyl cyclohexanol. At the same position itself, methyl is also present. So this acid catalyzed, I work plus OH2. This cleaves away. So I'll form plus and CH3. Two possibilities are there. As she is saying, I would have eliminated H plus from here. I would have formed a bond here to form this. What is another possibility? This itself would have went and it would have formed this product. Correct? But which is the major one here? They ask for the major. The more substituted alkene is the major product. So only this is the major product.
Ma'am, why is it the major product again?
The more substituted alkene will have more hyperconjugation structures or more alpha hydrogens will be there. That makes it stable. Did you understand?
But why is this not as stable as? I don't get it, ma'am.
Here, when you talk about the stability order of the alkene, that alkene which is having more number of alpha hydrogens leads to its stability. That means that one will be having a lot of hyperconjugations. Hyperconjugation is very similar to resonance. So you're having CC here. This carbon is having 2 alpha hydrogen. This carbon here it is having 3 alpha hydrogen, and again here it is having 2 alpha hydrogen. But look at this. This carbon is not having any alpha carbon at all. This carbon is having 2 alpha carbons. Compare which structure is having more alpha hydrogens? Obviously this structure. So more is the alpha hydrogens you have, they'll be able to go for resonance here. That is the importance.
So if a structure has resonance, it'll automatically be with the more major product.
Repeat.
If one has resonance and the other doesn't have resonance, the more resonance one will
Of
always
course,
be more major
more
product.
stable. Yes, of
Okay.
course. More resonance structures it has, more is the stability, and that will be a major product. Okay. Yes. We are going for the
Okay, ma'am.
commercial preparation of the alcohols here. The first one is methanol, which is also called as wood sprit. So this is done by destructive distillation of wood. That means I'm just combusting the whole wood and I'm getting it. That is what is called as destructive distillation. Today, most of the methanol is produced by catalytic hydrogenation of carbon monoxide at high pressure and temperature in the presence of this dual catalyst. Two catalysts are being used. Dual catalyst. So earlier it was done by destructive distillation of wood. Today you do it by catalytic hydrogenation. What is, ma'am? Hydrogenation means addition of hydrogen. Since I do it in the presence of catalyst, I call it catalytic hydrogenation. This is carbon monoxide. Okay. So this combination that you're seeing right now, carbon monoxide and hydrogen, carbon monoxide plus hydrogen is called as water gas. Methanol is colorless liquid, boils at certain temperature, it's highly poisonous in nature. We understood why it is poisonous because it gets oxidized by our enzymes to form formic acid. Ingestion, that means eating, having even very small quantity of methanol can cause blindness and even death. So where do you use methanol? Basically, it is used in the formation of formaldehyde. Because we know methanol, when you oxidize it, will form formaldehyde, right? So it is used for formaldehyde, paints, varnishes. The next one is ethanol. You commercially obtain it by fermentation process. That's the oldest method from the sugars. What you're seeing right now is sucrose. So sucrose in the presence of water, that means the hydrolysis of sucrose by the enzyme called as invertase. You can see the sucrose is getting split into glucose and fructose. Now this glucose in the presence of the another enzyme zymase gives you ethanol. Okay, so ethanol basic commercially we do it by fermentation from sugars. The sugars in molasses, sugar cane. That's the reason you call it sucrose itself, right? You get it from sugar cane. Or fruits such as grapes is converted into glucose. Fermentation is a biological process where the enzymes work. So it gets converted into glucose and fructose. In the presence of an enzyme invertase, it happens. Now glucose and fructose undergoes fermentation. in the presence of another enzyme zymase, which is found in yeast. So these two enzymes names are asked in MCQs. What is the role of zymase? What is
Ma'am,
the role
what's
of
the difference
kinase?
between glucose and fructose? They have the same chemical formula?
You'll be learning in biomolecule chapter. This is an aldehyde, aldohexose. This is ketohexose. It's a ketone. Because aldehydes and ketones are functional isomers, isn't it? So they will have same formula only.
Ma'am, can you repeat, your voice was breaking?
This is aldohexose, ma. This is ketohexose. We know aldehydes and ketones are functional isomers. Okay, so only they have the same formula. Am I audible?
Oh, yeah. Yes, ma'am. Okay, ma'am.
You didn't tell me your score at all. What happened to the test? What was your score?
Oh, yeah. Okay. Ma'am, I got good. I got 33 out of 35.
Wow, that's nice. Very good. What about you, da? Diksha?
I got 24.5 of 35.
Why?
I didn't expect like the strict correction. Like even if I missed like a small point, like ma'am would cut 1 mark or point 5 because of the OMS, new OMS thing. So like she was very, very strict in correcting, and I didn't expect that. So she got lots of marks in every single question.
But even Taksha would have done the same thing, right? I don't know.
She said that she analyzed her teacher and was able to tell like she would be a
Hmm.
strict corrector, but I just like got used to my previous teachers correcting methods, so I wrote like that. But like
Okay.
our current teacher right now is like you have to write everything very short and like all the points exactly, and you can't like write long
Mm-hmm.
rambling answers, which I did, and like she got
Mm.
marks for that as well.
For
So
writing it
yeah.
lengthy.
Yeah, for writing lengthy.
That's correct. That's usual. Mm. So can
Yeah,
you
I didn't
please send me
expect.
your question paper? Let us see your guys' question paper. Send me the question paper, okay? Is that possible?
Okay.
Yes. Ingestion of ethanol acts on the central nervous system. In the moderate amounts, it affects the judgment and lowers the inhibitions. Higher concentration causes nausea, even unconsciousness. Even at higher concentration, it interferes with spontaneous respiration and can be fatal. So they are just talking about the liquor, consumption of liquor, what and all it will do. All the consequences are provided here. So in wine making, grapes are the source of sugars and yeast. Definitely, every biological product is having its own enzyme in it. Your body is having millions of enzymes. Same way, grape is also having the enzyme. Okay, so grape acts as a source of sugar as well as yeast. As grapes ripen, the quantity of sugar increases and yeast grows on the outer skin. You could have seen this. Basically, when you are buying some fruit and you're just keeping it for quite a long time, not consuming it, you can see the decomposition starts. The decomposition is majorly due to this enzymatic action. And further, if it happens, then fungal action happens. It starts decomposing. Now, when they start ripening, the yeast grows on the outer skin. So when you crush it, sugar and enzymes comes in contact. Don't think it's a very easy process. Ma'am, I take a vessel. Today I will do it, ma'am. I put grapes into it. I'll crush it, ma'am. With a spoon, I'm going to separate out the enzymes and sugars out of it. It's not possible. You have to do different processes called as solvent extraction, distillation, crystallization. Many processes are involved in it to remove it. Okay. So, and the enzyme come in contact and the fermentation starts. So, when you start crushing it, when the sugar starts coming out, the enzymes comes in contact with it. So, what happens? The enzymes acts on this sugar, and this action is called as fermentation. Fermentation takes place in anaerobic condition. Very important point. Fermentation happens in anaerobic condition That means in absence of air, carbon dioxide is released during fermentation. Actually, there are two types of fermentation. I am not going to go in depth of it because it's not biology class. Aerobic as well as anaerobic. So if I'm going to do it in different, like aerobic fermentation, I get a different product. In anaerobic, I'll get a different product. The presence of air and absence of air. Okay, that's what they have mentioned here.
Oh, ma'am,
Hmm.
also I wanted to ask, we have our essays in like I
Hmm.
think 3 weeks,
Okay,
and we have the first chapter actually. We have haloalkanes and haloarenes. So will we be able to complete it in that time?
when is that?
1 second, let me check, ma'am.
We will be completing this chapter today itself. We're almost nearing it. In the coming 2 weeks, we will be able to complete that chapter.
Okay, ma'am.
Okay. Right.
Yes, okay, ma'am.
The action of zymase is inhibited once the percentage of alcohol formed exceeds 14%. So zymase is actually acting on it, where it is getting converting this glucose into ethanol. This gets stopped, inhibited, when the percentage of alcohol formed is exceeding 14 percentage. If the air gets into fermentation mixture, the oxygen of air oxidizes ethanol to ethanoic acid. Ethanol is already getting formed. If you're going to do it in vacuum in a very sealed container, it's fine. But if at all the air gets into it, it converts it into ethanoic acid, which in turn destroys the taste of the alcoholic drinks. Ethanol only gives that taste. If it converted into ethanoic acid, it is almost like vinegar solution. The taste is spoiled. Ethanol is a colorless liquid and the boiling point is 351. Look at the methanol boiling point. It was 337 Kelvin. So you can see there is a difference in their boiling point itself because the molecular mass increased. Boiling point is directly proportional to molecular mass. Since the molecular mass increased, its boiling point also increased. It is used in solvent, in paint industry, and in preparation of number of carbon compounds. It is very usually used. The commercial alcohol is made unfit for drinking by mixing in it some copper sulfate to give it a color, and pyridine, a foul smelling liquid. It is known as denaturation of alcohol. Please mark it. Very important question, how the alcohol is denatured. That means you are spoiling the nature. Why should I spoil the nature? As I mentioned you in our previous class, those who are working in the beverage industry or the liquor industry may just take it to their home or they will be consuming it. The illegal businesses would start. To stop this, they denature this alcohol. So they had copper sulfate to give it a color and pyridine to add an unpleasant odor to it. Nowadays, large quantities of ethanol are obtained by hydration of ethene. So we are seeing the fermentation processes. Okay, we are seeing the fermentation process. But today we are not waiting till that time because fermentation takes quite a long time. It's not a faster process, but it is a very efficient process, but not a faster process. So we do hydration of ethene. I have CH2, double bond CH2. I'm going to add H plus in the presence of water. What will you get? You'll get CH3, CH2OH. We have done it several number of times, the mechanisms and all. I'm not repeating it again. Okay, va?
Okay, ma'am.
Right. We are moving for ethers. R O R group. This functionality is called as ether, alcohols, and ethers or functional isomers. I have CH3, CH2OH, which is nothing but CH3O, CH3 as well. So how do I prepare it? As I mentioned already, I have ethanol. I treat it at 413 Kelvin with sulfuric acid. I form ether. Okay. So alcohols undergoes dehydration in the presence of protic acids. The formation of the reaction product, alkene or ether, depends upon the reaction condition. Yes, If I do it at higher temperature, it is alkene. If I do it a little bit lower temperature, it is ether. Where do you use this diethyl ether? Very commonly, inhalation anesthetic. Very previously, like decades back, they used chloroform as anesthetic. But chloroform is deadly anesthetic. It could be fatal also. So today we are not using chloroform. Instead, we move slowly. They went on to diethyl ether, this compound. Inhalation anesthetic. When you inhale, you will get anesthetic feel. But due to its slow effect and an unpleasant recovery period, it has been replaced by an anesthetic by other compounds. So today we are not using diethyl ether as well because it takes quite a long time. It's very slow in its processing, and when you recover, the recovery is unpleasant. I don't know whether you have had anesthetic previously. The recovery from the anesthetic is actually terrible. It's really terrible. You feel nausea. You feel very giddy when you're getting out of this anesthetic. So they are not using diethyl as well. Instead, they are using another type of compounds for it. The replacement has come upon. Okay, so you're looking at the mechanism here. I have alcohol. I treat it with H plus. For attack, I form plus OH2. Now another mole of ethanol. That's the reason you write 2 moles of ethanol, CH3, CH2OH, at con H2SO4 at 413 Kelvin is forming this diethyl ether. So this nucleophile is attacking this carbon so that water moves out. Now this oxygen lost its lone pair, so it gains a positive charge. In order to remove the positive charge, this H plus moves out so that this bond pair goes to oxygen again, so that you form an ether. Okay?
Yes, ma'am.
Yes. So this method is suitable for the preparation of ether having primary alkyl groups only, very important. CH3O, CH3 I want, you can do. But instead, ma'am, I want to do like this, ma'am. This kind of compounds are not possible for us by this method. The alkyl group should be unhindered, very important, like this, not like this. And the temperature should be kept low as well. Otherwise, what will the reaction do? It will favor the formation of alkene. The reaction follows SN1 pathway. Yes, it is following SN1 pathway. You can find you are creating a carbonium ion here. Once it is moving out, what will happen? You will form CH3, CH2 plus. Now the nucleophile is attacking it. Okay, so it's following SN1 pathway when the alcohol is secondary or tertiary, about which you will learn in the higher classes. So definitely not now. So when I am talking about secondary here, in this reaction, in this step, you can see the direct attack is happening and you are going for the direct reaction. This is concerted mechanism where there is no intermediate formation. But in case I'm having like this, man, secondary alcohol is there. In that case, this will move out to form carbonium ion. Okay, I repeat, the reaction follows SN1 pathway when you do secondary and tertiary alcohol. However, dehydration of secondary and tertiary alcohols to giving corresponding ether is unsuccessful. I am able to do for a primary alcohol. This is successful. For secondary and tertiary, it is unsuccessful because for secondary and tertiary, instead of ether formation, what will it form? It will form alkene. Understood, right? We are moving
Okay,
for the
ma'am.
next
Yes,
synthesis
ma'am.
called as Williamson synthesis. A synthesis in which you take an alkyl halide, you treat it with sodium alkoxide. What is alkoxide? I have an alcohol. When I treat it with sodium metal, it forms RONA plus half a mole of hydrogen gas. This is called as alkoxide. Since sodium is there, I call it as sodium alkoxide. So I take an alkyl halide, I treat it with RONA. Look what's happening. NaX is removed so that it's forming ROR. This synthesis is called as Williamson synthesis. You can prepare both symmetrical as well as unsymmetrical ethers here, very important. Ma'am, I'm having CH3X. I'm treating it with CH3ONA. you form dimethyl ether. In case I take CH3X, I am having CH3, CH2ONA. Here it will form CH3O, CH2, CH3. This is symmetrical. Both the places CH3. Here it is unsymmetrical. This is methyl, this is ethyl. So Williamson synthesis is useful for synthesizing unsymmetrical ethers as well as symmetrical ethers. Understood, pa?
Yes, ma'am.
Definitely you don't need this part, so I'm skipping that. Ethers containing substituted alkyl groups. What do I mean by that? Secondary or tertiary may also be prepared by this method. You can also prepare them. The reaction involves SN2 attack of an alkoxide ion on the primary alkyl halide. The very important thing is that I can use CH3X plus CH3ONA to form CH3OCH3 in case. Ma'am, I'm having CH3 thrice X, ma'am. Here I'm having CH3ONA. Will this also form CH3 thrice OCH3? No, you won't form this. I repeat, primary alkyl halide plus sodium ethoxide. Sodium ethoxide is a very strong base actually. Here, since the even if I'm going to move it like this, if I'm creating a positive charge, it is just a methyl carbonium. It's not that much stronger, correct? So therefore, it is an acting for an SN2 attack, direct attack. O minus CH3 attacks and this moves out. One pathway. In case I'm having secondary alkyl halide or a tertiary alkyl halide, let me say, ma'am, I'm having CH3 thrice X plus CH3ONA. In this case, uh, let me say, like this it is. I'm treating with CH3ONA. Here, if I'm eliminating this X, I'm able to generate a tertiary carbonium ion. Very stable, na? So here what would happen? One of the hydrogen from here would move out so that you form an alkene. Please make a note. Williamson synthesis can use primary alkyl halide. But if you are using tertiary alkyl halide, it will lead to formation of alkene. If I use secondary alkyl halide, there is a possibility of forming the both ether as well as alkene. Is that clear, pa?
Yes,
Yes,
ma'am.
ma'am.
All right, ma'am. So here they are using this tertiary alkoxide. Doesn't mind. Tertiary alkoxide is not a problem, but your alkyl halide should be primary. I repeat, look at these two cases. Here it is primary alkyl halide. Here it is tertiary alkyl halide. This is my base. This is my base. Alright. So in this case, what did I tell you? It will form alkene. In this case, it formed an ether. Clear na? Please make a note of it. Better results are obtained if the alkyl halide is primary. In case of secondary and tertiary, elimination competes over the substitution. If tertiary alkyl halide is used, an alkene is a only reaction product and no other ether is formed as I mentioned. If it is primary alkyl halide, you have ether. If it is secondary alkyl halide, you have ether as well as alkene. If it is tertiary alkyl halide, you will have only alkene. Clear?
Ma'am, so for secondary, it will be like a major minor product, right?
Yes, yes. Alkene will be your major and this will be your minor.
Okay, ma'am.
It is because the alkoxides are not only nucleophiles. Because, ma'am, I see this is CH3O minus. When you compare with OH minus, it is a base also. Even it can act as a nucleophile also. Both the things are possible. They are not only nucleophiles but also stronger bases. So depending upon your reactant only, they will decide whether I can act as a base or I act as a nucleophile. Clear na? They are asking
Okay,
you the
ma'am.
following is not an appropriate reaction for the preparation of tertiary butyl ether. What is tertiary butyl ether? It is an ether. Okay. Tertiary butyl it is. The smaller number of carbon only you add it with this ether. We have learnt it in the IUPAC nomenclature. This is not IUPAC in here. It is common name. The smaller number of carbon you add it with ether always. So I understand there is OC2H5 and it is tertiary butyl. This is tertiary butyl. Tertiary butyl ethyl ether. They are telling you this procedure is not possible. Why? Because what are you using here? You are using tertiary alkyl halide, isn't it? Will it form an ether? Can it form an ether?
No, I can only form alkene.
Alkene, right? So it's not possible. So they're asking you, then what should be your possibility here? If I'm going to use it, I'll form only alkene, isn't it? If I'm using tertiary alkyl halide, what will I form? I'll form only alkene, like this. Correct, na?
Yes, ma'am.
Yes,
Right.
ma'am.
So they're asking you, okay, I wanted to provide tertiary butyl ethyl ether. Same thing. Give me the reactant. Here, ma'am, I can use alkoxide as a tertiary group. Nothing wrong in it. Then I have, then I can use primary alkyl halide. Nothing wrong in it. Here I can form ether. Repeated question. Clear? The next reaction is with phenols. I convert the phenol into aryl alkyl ether. It's an aryl, this is an alkyl, and I'm having a ether unit here. OH. The presence of sodium hydroxide forms ONA. So isn't it like a Williamson synthesis? RONA plus RX is giving you ROR, correct? So here you can see NaX is removed and I am forming OR.
Ma'am, what is phenoxide moiety?
Moiety means molecule structure. Here I made it as O minus. This is phenoxide. Moiety means it's a structure, molecule.
Okay, ma'am.
Okay, next now going for the physical properties. Look at the boiling points here. N-pentane, ethoxyethane, butane 1-ol. Right? So it's a mere hydrocarbon it is. Definitely its boiling point should be in between the ether and the alcohol. Can I say that? Because ether is completely least polar. Correct? It is highly polar. Ma'am, when I'm comparing hydrocarbon and ether, don't you think ether is at least polar? It is completely non-polar. Then how can it have 309.1? Can you justify this? Can you understand my question? If I compare the polarity of ether versus hydrocarbon, definitely it is completely non-polar. It is at least polar. And how come this is having higher boiling point than ethoxyethane? How many carbons do they have?
Um, they have the ethoxyethane. Oh, wait, yeah. This is only ethoxyethane has only four
4
carbons,
and this
but
is
this one
having
has
5 carbon. That's right. So more
five.
is the number of carbon that leads to its higher boiling point. But still you can see it's not that much huge differences here. 309 and 307. But here it is 390. Too much difference you can see. Okay. So CO bond in ethers are polar and thus ethers have a net dipole moment. Why should ether have a dipole moment? I am saying not. I didn't say it's non-polar. I said it's least polar. That's the reason why it's having a net dipole moment. That is something it's available. The weak polarity of the ethers do not appreciably affect them. their boiling points, which are comparable to those of alkanes of comparable molecular masses. When you consider their molecular masses are almost comparable. That's the reason why they are having almost approachable boiling points. But it is much lower than the boiling point of alcohol. Why? Why alcohol has high boiling point? Why do you think alcohol has more boiling point than ethers?
Because it's polar.
Just that? Because it can form hydrogen bonding. It can go for hydrogen bonding, isn't it?
Oh,
So a large difference in the boiling point of alcohol and ethers due to the presence of hydrogen bonding in alcohols. So always remember boiling point is directly proportional to molecular mass, is directly proportional to hydrogen bonding. Now we are talking about the miscibility, how much it will be soluble. It resembles those of alcohols of the same molecular masses. How much it will be soluble. Both ethoxyethane
Ma'am, can you scroll up a bit? Boiling point is directly proportional to molecular mass and
and hydrogen bonding.
oh, okay.
In the hydrogen bonding, if it is doing intra, it will have low boiling point. If it is doing inter, it will have high boiling point. Both ethoxyethane and butanol are miscible to almost the same extent. You can see that here. Almost, it doesn't mean it is the same. Look at the difference. It is 7.5 and this is 9 gram per 100 ml. Because methanol can make hydrogen bonding, still more solubility is possible. It's also more polar compared to ethoxyethane. So only 9 grams is soluble. Here only 7.5 grams is soluble. While the pentane is essentially immiscible with water because it is completely non-polar. It cannot form any hydrogen bondings also. So it's ultimately immiscible with water. Okay.
okay, ma'am.
You can see why they are able to form, why at least they should be soluble like alcohol. Because when I said alcohol, ROH, they can form hydrogen bonding. Similarly, here also they can form hydrogen bonding. But this hydrogen bonding is not that strong like this hydrogen bonding. Because there are two R groups here. Bulkiness is there, more plus I effect is here, which decreases the strength of the hydrogen bonding. Okay?
Okay, ma'am.
Right. We are seeing the chemical reactions of ethers now. I'm having ROR and HX. So where you can form RX and ROH. Ethers are least reactive. Basically, they're very least reactive functional groups. The cleavage of the CO bond in ethers, this bond, takes place under drastic condition. Not like simple. You have to use excess of hydrogen halides here. Too much you have to use. Okay. And then only the reaction would happen here. You can see when I take alcohol, I treat it with HX. What will you form? RX and H2O. This is easy, but this is not that much easy. Alkyl aryl ethers. Aryl I have, alkyl I have, and it's an ether. Cleaved at the alkyl oxygen bond. This place. Due to the more stable aryl oxygen bond. Because still a very common question. OR is there. I treat it with HX. What is your possibility? OH and RX is my possibility. Why, ma'am? Why can't this I break this bond here. Why do you think I should break the bond here? Because you say it is OH. Why don't I break it and I say it is just benzene? Because this bond is stronger compared to this bond. So only I don't break this bond. Instead, I break this bond. Clear that?
Yes, ma'am.
Yes,
Yes.
ma'am.
Ethers with two different alkyl groups are also cleaved in the same manner. ROR-HX is there. So I have RX and R-OH. In here, if I am having a possibility of more stable carbonium is possibility is there. In that case, that X will go and join with that R only. Let me say I'm having CH3, CCH3, CH3, OCH3 is there. Where will this X go and add? The X adds here and the H adds here. So I'll have like this. Do you understand this? I have an ether. I treat it with HX. Where will this X minus attack, ma'am? If you are having the possibility of doing more stable carbonium, let me say I'm breaking it like this. I have H plus and X minus. If I'm breaking it like this, what should happen? I will create a positive charge here and negative charge here. The positive will be attacked by X minus and the negative will be attacked by H plus. Please make a note of it. Two important questions. When you are having aryl alkyl ether plus HX, you will not break the aryl oxygen bond, which is stable. You are having an ether and you are treating with HX, unsymmetrical ether. If you can form stable carbonium ion, make it and attack the X minus there. Shall we continue? Is that done?
One second, ma'am. Ma'am, so the reason where
Hmm.
X minus goes there is because positive and negative if you break the bond.
Yes, yes. Okay.
Okay, ma'am.
Right. The order of reactivity of hydrogen halides. Hi greater than HBr greater than HCl. Why is this? Because you know this I minus is a very good leaving group compared to Br minus compared to Cl minus. Due to the leaving group ability, I have Hi greater than HBr and HCl. It's very usual that cleavage of ethers basically happens in concentrated Hi and HBr at high temperature. It's very rare that you are being provided HCl because we know that ether by themselves are very least reactive. So in order to make them activated, you need stronger acids here. For that, I use Hi and HBr, the two concentrated acids at high temperatures.
Ma'am, isn't HCl more reactive though? So won't it like help the reaction occur more faster?
No, when you're comparing the strength of the halo acids, HF, HCl, HBr, HI, the acid strength increases down the group. The reason is
Oh,
that I is
okay, ma'am.
least electronegative, it will be able to release H plus so easily.
Yeah, that makes sense, ma'am. Okay.
Yes.
Okay, ma'am.
I'm just showing you the ethers reaction here with HI. So I'm having lone pair. Lone pair attracts the H, becomes O plus H. Now I minus is here. So where is this I minus going to attack here? That's the point. I'm having methyl here, I am having ethyl here. Where will it attack? This I minus always chooses a smaller unit. because it's a nucleophile. Definitely this doesn't like a nucleophile. It itself is having 2 plus I groups. So what happens? I minus attacks the CH and this bond cleaves. So they form an alcohol and alkyl halide. The reaction of an ether with con-HI starts at protonation of ether molecule. The reaction takes with HBr or HI because these reagents are sufficiently acidic, as we just mentioned. Acid strength. Iodide is a good nucleophile. It attacks the least substituted carbon of the oxonium ion. You can see this is oxonium. Oxonium is that oxygen which is carrying positive charge. So it's attacking this least carbon containing fragment and displaces an alcohol by SN2 mechanism. Okay. Why do I say SN2 mechanism? Because I haven't created any carbonium ion here. If I created carbonium only, I say it is SN1. There is no carbonium at all. You can see the nucleophile is attacking and this